last lecture, we had looked at solving a tridiagonal matrix system. In this particular lecture, we're going to focus on solving a Poisson equation. So, the general form of the equation is the Laplacian of u is equal to some function. And we're going to solve it on a two-dimensional domain. So, if you recall, we had solved this particular problem in Python, and we had made use of a structured grid. We had discretized this Laplacian using central differences. So just to recap, the Laplacian is del 2 del x2 plus del 2 del y2, and the approximation, the finite difference approximation. So if this is the I direction and this is the j direction, then at the node I comma j, del 2u del x2 can be written as ui plus 1j minus 2uij plus ui minus 1j divided by delta x square. Similarly, del 2u del y2 can be written as uij plus 1 minus 2uij plus uij minus 1 divided by delta y square. So it makes use of these four neighboring points. So in the terminology of PETSc, this particular stencil is called as a star stencil. There is one more stencil in PETSc that is called as a box stencil. It makes use of these points as well. In this particular case, we won't be needing it, so we'll be focusing on the star stencil. So let us get started with the program, and as we go through the program, we'll discuss the various terms and keywords as and when they appear. So let us start. So first things first, we must include petsc.h. Let us save the file. So let me call it poisson.c. Alright, so then we must obviously have the main function. So int main, then int argc char star star arg v. This is just to pass command line arguments. Alright, so now we must, as usual, do two things. One is return petsc finalize, and we must begin with petsc initialize. Alright, so petsc initialize as usual takes the arguments, so we'll copy it from our previous program. Alright, so this will be solve Poisson equation in 2D. Alright, so once we've done this, we must declare something which is called as a Dmda. So Dmda, the data structure Dmda, so the full form, there's no agreement on what this full form should be, but it is good enough if you can think about it as distributed member, or data management. There are various things. And the last thing is distributed array. So DMDA could stand for any of this. I'm not sure what it is, but essentially it's used for a structured grid, as opposed to the case of an unstructured grid that one uses for problems which have complicated geometries, infinite element methods, and so on. So where you have unstructured grids, but here we will focus on a structured grid. So DMDA is a PETSc data structure which allows us various, I mean, not shortcuts, but it helps us in creating the finite difference matrix A, where A times the unknown is equal to B, the right hand side. So it helps us in constructing this without having to work a lot towards it. So we must create this DMDA matrix. So let us do that. So first we must declare dm as a variable dA. Then apart from this, we'll also need the matrix A. We will need the vectors B and U. We'll also need the solver KSP. So these things we have discussed already. And apart from this, we'll need the error. So double ERR. Okay, apart from this, one more utility is DMDA local info. So it's a data structure which holds information about the structuration of the grid. In particular, it will tell us the bounds of the grid, and it will help us in performing loops. So this is a very useful data structure. Alright, so now that we've done this, we can go ahead and create the DMDA and declare it over the matrix A. So DMDA create 2D. So obviously you can imagine there's a 3D version as well. So the syntax is, first we have to pass the communicator, the MPI communicator. Then we must pass the nature of the boundary. So in this case, the nature of the boundary will be none. There is no special thing we have to do about the boundary. And if the boundary is periodic, then you must supply DM boundary periodic. Otherwise, it's good enough to have this. Then we must tell what kind of grid we will have. So in this case, we're going to have a star stencil. So DMDA stencil star. Then finally we must, so what we can do is declare a default size. So 9 cross 9. And finally we must pass the subdivision of the 9 by 9 grid. So like in the previous examples, we will ask PETSc to help us in balance the load. So it should be PETSc decide. PETSc decide. So it's for both x and y directions. Then, so let me open the syntax real quick. It will be clear what is going on. Okay, so we have done this. Then we have to pass the degree of freedom. So degree of freedom meaning what is the, so if it's a scalar, it has only 1 degree of freedom. Then you have to put the stencil width and so on. So stencil width will be 1. The degree of freedom will be 1. That's why we have 1 comma 1. Then we have to say arrays containing number of nodes in each direction. So if in general you will simply set it to none. Okay, we don't need to have the number of nodes. So it will be none, or rather null, then again a null, and finally we must pass the address of the DM object. So that's the final thing that you need to pass, right? So this is how we create a grid. So that's it pretty much for creating the object. This is what you need to do. Now let us go ahead and create the matrix. So we can, no, rather not the matrix, but let us proceed with the DA first. So DM set from options DA, and this is important if we want to pass command line arguments on how large or how small we want the stencil to be. If we don't care, I mean, you have to do this, otherwise you cannot pass any command line arguments. Then DM setup DA, it's the same as the routine for setting up a matrix or a vector. Then DM create matrix. Now this step is quite important because it will tell the function that this structured grid has to eventually pass its arguments to A. Note that we don't need to worry about the size of A, because depending on what this grid is going to be, the size of A will be automatically fixed. And why is that? Because if there are m cross, if it's a grid of m cross n size, then the matrix size will be m cross n cross m cross n. If m and n are equal, so if it's a 9 by 9 grid, then the number of variables will be actually 81. So it's m square by n square in this particular case. So A will automatically be sort of linked to this structured grid, so we don't need to worry about that anymore. And finally, mat set from options A. So this is where you sort of create the matrix A. All right. So once we have this, we can now create the vectors. So what we can do is DM create global vector DA, and we'll pass the address of B. Then we will do a vec duplicate DA comma the address, not DA, it has to be B comma address of U. So this is just to initialize U, and in, because eventually we want to compare the solutions, let's make it U exact. So U exact will hold the exact solution. So let us create another duplicate B comma address of U exact. So far we have created A, B, U and U exact. Based on this we have to proceed. So now at this point we have sort of linked A to the DA, we have linked B to DA, we have linked U to DA, and we have linked U exact to DA. What needs to be done is we need to do multiple things now. We need to form the exact solution for future reference. Then we need to form the matrix A. We need to form the RHS matrix vector B, and finally we need to solve it. So how do we solve it? Again, it's the same as before, and in this case we can reuse some of the code. So this particular code will be useful. So we'll simply have KSP create PETSc world, pass the address of the KSP object, then KSP set operators, KSP A, the preconditioner is going to be A default, set from options KSP, then KSP B comma, instead of X we will now have U. All right, so this is the entire thing, but now we need to focus on writing these things. But before even doing that, let us quickly free the vectors before the code finishes. So vec destroy, pass the address of u, copy this, u exact, b mat destroy a. What else do we have? Not a, but the address of a. Then we have ksp destroy address of ksp. Finally, we have additional dm destroy address of da. And then finally, we have return PETSc finalize. So that's as usual. So now we must go ahead and write down these functions. Alright, so like we had done in the case of the code that we did in Python, we're gonna assume a solution u, xy is the exact same solution. You can compare it later on. So it's x square minus x to the power 4 times y to the power 4 minus y square. It's a function which satisfies the Dirichlet boundary conditions on a unit square. This is 0 comma 0, 1 comma 0, 1 comma 0 and 1 comma 1. So it satisfies the Dirichlet boundary condition u on the boundaries. So on the boundaries is equal to 0. Alright, so what we need to do is encode this into the u exact vector so that we can later on compare it. Alright, so let us create that function. So let us create that function. So let us make the return value PETSc error code, and we have used this IERR. Actually, I've not been using it over here. Each function call can be something like this, and then we can do a ERR chq of IERR. But I'm not doing it. You don't need to do it. But in case you need to make a large program, we need to debug, you need to do all that, and then you have to declare the PETSc error code IERR over here. And we've done it in the very beginning, but I'm not going to do it over here. So let us create a function called as create u exact, and it will take as an input the structured grid dA and the vector u exact. So u exact has not been initialized. So the purpose of this particular function, that is u exact, is to initialize it and have it available in the main as well. So we're passing the vector, we're going to modify the vector. So essentially this is the input and this is both the input and the output. The input is coming in as nothing, but the output will be the exact value. Now we have to loop over the grid, because look, whenever we want to calculate this, we need to know how the loop will go on. We need to know how many grids have been initialized. Well, we have created 9 by 9, but you can pass command line arguments and change it. So over here we're gonna create another local copy of dmda local info. We're gonna call it as info. So note that this particular local copy does not conflict with this because of the scope of this function being different from the scope of the main function. Then we're going to define int I comma j for running the double loop, and we're going to create hx hy, because hx and hy are simply the grid spacing. We're going to create x and y, and we're going to create a double pointer which will act as an auxiliary a matrix to store u exact. So basically what we're going to do is, see, u exact is a vector. So in the PETSc data structure, it's going to be a vector, but in reality u exact is a matrix. It has values all over the grid. So what we can do is we can swap between this 2D representation, which is in the form of a double pointer, because arrays or rather matrices in C are in the form of double pointers, and we can um, co- convert back and forth between the vec structure of PETSc and the matrix structure that we require in C. So for that we need to create a double array, and the double array we'll call it AU exact. So A stands for the auxiliary matrix for that. Alright, so Dmda get local info is the function which picks out the information from the structured grid DA and passes it on to the variable info. So now what does info have? Info has two things. One is info.xm, then it has info.xs, it has info.mx. So info.mx is the maximum. So if the grid has mx number of points, so the grid will go from 0 to info.mx minus 1. That is what it means, right? So we must run a loop going from uh, info.ys. So what is rather not ys, xs is like the starting point. So if one processor is dealing with only this thing, so for this the local starting index for that processor will be info.xs. Okay, it's like a local starting index, and this particular last index will be info.xs plus info.xm minus 1. This will be the ending index. So let me just go to the function reference. So what is it? Dmda get local info. Dmda get local info. So it contains all these things. So it's the global number of grid points. So it's a structure, it's a data structure which contains all these informations. So the dimension, the degree of freedoms, right? Then we have the global number of grid points. For that processor, what is the starting point? For that processor, the number of grid points. If you have ghost nodes, okay, type of ghost nodes, the stencil, the DA, and all this thing. So for our purpose, we can make do with the starting point of that particular processor to the end point on that processor, rather the number of. So that's why we have plus. So number of grid points plus starting point will be the final point, and minus 1 will be the index of that point. Okay, that's why this minus 1, because it's the index of the ending point on that processor. If you're using one processor, then it's the maximum value minus 1. So just think about it, why it will work. So before that, let us create hx is equal to 1.0 divided by info.mx minus 1. So look, info.mx is the maximum number of grid points. So this grid spacing will be this. Hy will be 1.0 divided by info.my minus 1. So these are the two hx and hy. Accordingly, we can now define rather x as I times hx and y as j times hy. Okay, the same thing we had done in Python as well. All right, so let's do a loop for j equal to info dot ys, j less than info dot ys plus info dot ym. Let's just create a bracket just to be super sure, and j plus plus. Let's now create another for loop for I equal to, so let me just copy this. We just need to replace everything by the x. So this will be xs, this will be xs, this will be I, oops, this will be xm, and this will be I plus plus. So there's a huge chance you can mess this up, because if you forget to change one I or one j, all the loops will run incorrectly. So before entering into this, let us just define y equal to j times hy. Before going into this loop, let us define x as I times hx. Great. So then what we can do is we can say au exact j comma I. So the jth row, ith column is equal to the exact solution, which is x square minus y square x times x square minus x to the power 4. So this is it, times y to the power 4 minus y square. Alright. I mean, you could use power and all that, but it's okay. It's a simple example. We can get it done like this as well. So that's the analytical solution, what we have written over here. Right. So now that we have defined the u exact as a two-dimensional grid. Okay, look, this variable is actually a two-dimensional grid right now. So what we have to do is assign that grid to the vector u exact. And the way to do it is dmda vec restore array over dA u exact and the address of au exact. This particular line, right, this particular line will tell the function that look, u exact is a vector based on the structured grid dA, and this is the actual matrix u exact which is based on the structured grid dA. So it will do the interconversion for you. Essentially, it will flatten out the solution in the form of a single vector. It will take all these entries and flatten them out into a single vector. That's what it will do. And finally, if everything is successful, let us simply return 0. Right? Good. So that takes care of PETSc error code u exact function. Right. Now let us create a function which will create the right hand side. So PETSc error code form RHS, and we'll also need a function PETSc error code form matrix. So these are the two functions we still need to write. And so what should these things contain? So let us first look at, I mean, we've done this for the case of Python already, but still let us have some, for completeness, final equation looks something like this: minus of twice 1 minus 6x square y square 1 minus y square plus twice 1 minus 6y square x square 1 minus x square. So how did this thing come into being? Well, we made use of the fact that we know the exact solution u. Okay, so the equation is this equal to minus f, and we know that the solution u is x square minus x to the power 4 times y to the power 4 minus y square. We know that this is the solution, so we can plug this into this and find out the function f which satisfies it. So this is the function that satisfies it. All right. So on the left hand side you have u I plus 1 j plus u I j plus 1 minus 4 u I j plus u I j minus 1 plus u I minus 1 j is equal to minus of this f times h square. Well, let us assume that hx and hy will be equal for uh, for for this particular specific case. I mean, we don't want to make it too general, otherwise it will create nothing. We just have a ratio of hy by hx square appearing somewhere over in these terms. But anyway, for now we can go ahead with this assumption, and it's fair to have a structured grid with equal points in both the directions. So what is the right hand side? So the right hand side is simply gonna be h square times this function f. Well, what we can do is take this minus sign over here. So this becomes minus, this becomes minus, this becomes plus, minus and minus. So we have this is equal to this right hand side. So this vector A will be constructed as per this left hand side. And so because it's gonna be u, ij, all the elements u, ij's, right hand side will be simply f times h square at the point ij. So we can first go ahead and create the function form RHS. So again, what are we going to require? So we're going to require two iterators I and j, then double h comma x comma y comma we can create f, and a matrix to hold the value of the right hand side over all the grid points. So once again, eventually what you're going to do is convert this matrix, because once again I'm going to reiterate this, no pun intended. So we're gonna have the right hand side at all the grid points. Right, we're gonna essentially have the right hand side on all the grid points, and we have to convert this into a vector structure which is there in PETSc. So the inputs will be the dm, da, and the vector b. That's gonna be, I mean, these are not the inputs, but these are just placeholders for the input. When we call the function from main, we're gonna call it as form RHS da comma b. This is just the declaration of the function and the definition inside. Right, so these are things, I mean, quite usual to C programs. All right, so now we have to create this RHS function. So let's do this. So double we've defined, we will need the dmda local info, we'll call it info. Again, this scope is different from the scope of the previous function and main both. All right, then we actually need this double loop. So let's paste this double loop, we're gonna need it anyway. So it's gonna do this. Instead of having this two declarations, we're gonna just keep one declaration. J loop remains same. Instead of hy and hx, we simply have this, and a b j comma I will be equal to then f times h square, where f will be equal to 2 times, now what is that big term, this whole term. So what is it? Let me reduce this in size. 2 times 1 minus 6 times x square, we make it into a bracket, times y times 1 minus y times y. Let me copy this, because the other term is simply x and y swapped. This will be plus this. So what do we have? 1 minus y times x times x, x times x. Alright, so this is what f is, and the right hand side is f times h square. All right, great. So lastly, what should we do? We should restore this double matrix to the vector B. So we must do dmda vec restore array, and we must pass the dA, B, and the address of the double matrix. Great. Lastly, we must return 0. So that takes care of the right hand side function as well. And now it's simply a question of creating the matrix. And that's quite simple given we have done the creation of the vectors. This should be not that difficult. So dmda local info. Again, we're gonna need int I comma j as the iterators, double h. Now we have to insert 5 elements, 1 2 3 4 5. So each row there will be 5 insertions into the matrix. So we must create a value matrix which is of size 5. Yeah, and apart from this, because we're gonna fill in the matrix, there is an additional data structure called as mat stencil. We will create it as row and call, we will have 5. So it will sort of link the DA and the matrix A. So we have to tell, we have to pass this mat stencil structure into the mat set values. So once I write the code, I will explain it how it works. Before that, I can just show you the quick function reference, or rather the data structure reference. So it's a data structure for storing information about a single row or single column of a matrix. So row I comma j, column I comma j. So those ij's are from the actual grid, but row will calculate the linear index from I comma j, and column will also calculate the linear index from I comma j. So it's just allowing you to seamlessly do those linear indexing business without having to write any extra code. Essentially, you're still looping over you're still doing a loop over nothing but the grid, but you are able to pass the appropriate index to the matrix A, right? So that's quite beneficial, right? So we've created this. What else do we need? Okay, we'll declare everything that we need as we go along. So dmda get local info, pass the information from DA to the address of info. Again, this info is local. So essentially we've done this line. We also need this particular line. Alright, then we're gonna actually need this particular double loop as well. Alright, but now in the double loop we have to do something else. So this goes. Alright, so now what should be the inputs to the function? It has to be the dm da and matrix A. Right, so yeah, so now we must do something over here, and at the end of the column loop, so this is the column loop, at the end of the column loop we must set values. So mat set values stencil, and this particular mat set value stencil actually links the setting of the matrix A from the grid points, right? So we must do this. So first of all, what does this contain? Mat set from mat set value stencil. Oops. So we must give the matrix the number of rows being entered. So we're gonna insert one row at a time. Then what do we have? Okay. Then what do we have? We have the ID, the address server, the number of columns being entered. So for the interior points it will be 5. For the boundary values it will be only 1. Alright, then PETSc scalar and insert mode. So it's quite similar to whatever we have done. Great. So mat set value stencil. This will contain a one row. We will pass the address of row. Now we must tell how many columns we're gonna insert. So let us create n calls as the number of columns we want to enter. So then we must pass the address of the, not the address, call, because call is already a pointer. Then the v array and insert values. Yeah, that's pretty much it. Now there must be a logic over here how to find out how many number of columns you have to fill. So for the interior points you have to only fill so you have to fill 5, but otherwise you need to fill 1, right? So we must declare n calls as an integer as well. So n calls is an integer. Great. So then what do we do? So for this we don't need x and y anymore. We don't need it. Then okay, so row dot j is j, row dot I is gonna be I, because we are focusing on this. So column is actually a vector, so column 0 dot j will be equal to j, column 0 dot I will be equal to I. So this is just to tell that based on this row and column you figure out the linear index. Don't make me do that. Okay, so both these lines will figure out the linear index. All right, so now we will start with n calls equal to 1. So if nothing else happens, we will through this simply set the diagonal element. So just a quick recap, what will be the diagonal element? If you've answered the linear index corresponding to this, which is I plus nx, or rather mx times j, you're absolutely correct. So it will put the value v0 into that element if we leave the code at this juncture. But what should we do? If I is equal to 0, right, or what? So this is the x equal to 0 point, or if I equal to info dot mx minus 1, or j equal to 0, or j equal to info dot my minus 1. So essentially these are all the boundaries. Now what we have to do, if I is this, if j is this, then we must simply set v0 to 1. We don't need to do anything else, and simply this particular function, when it executes, it will enter 1 in that particular location corresponding to that grid, the boundary grid, and we're happy. But if this is not the case, right, if this is not the case, then we have to do something else. We have to do something else. Well, so we must do v0 is equal to 4, then so that's it. So now if we are in the neighborhood of a boundary, then again we must do something special. So I request you to look at, work it through. Whatever I'm gonna write, you need to really work it through. So this is for an interior point, but if you have to deal with boundaries, you must check whether you are near a boundary. So if I minus 1 is greater than 0, that is if you are not at the left boundary, then you must do something, and that something will be call of n calls dot j will be equal to j, no problem. Call of n calls dot I will be I minus 1. Oops. Then call of n calls yeah, n calls is 1. So when we are entering into this particular thing, n calls is 1. So we are setting it to, so we have already set the call 0. So we are setting the call 1. Right, call dot n calls dot I will be I minus 1 and value will be 1. Well, n calls will be equal to 1. And in the end, if this is satisfied, then we must increment the n call by 1, because we will again check whether it is not near some other boundary. So if I plus 1 is less than info.mx minus 1. So this is just to check whether you're not near the right boundary. If you're not near the right boundary, then you can set the columns corresponding to that particular boundary as well. So this will be still j, this will be I plus 1, and this will be 1, and n call will be incremented. Then similarly we can copy these two conditionals and we can paste it. So we have to check whether you are not at the lower, or not at the lower boundary, meaning you are not at, so if this is the grid, I just think I should iterate this because the value of u is 0 everywhere. So if you are at this, another at this boundary, then you need contributions from this neighbor, this neighbor, this neighbor, but not this neighbor because it's 0, right? That's why I'm setting it like this. Okay, so if you're not at the low boundary, then this will be j minus 1, this will be I, and the value will be 1, n call has to be incremented. And lastly, if it is not in the neighborhood of the top boundary, then you can do this and you can do this. Alright, so far we have created everything. We have accounted for the fact that the value at the boundaries is 0. At the end of this loop, we can now set the matrix. So let's take stock of whatever we have done. Yeah, we have done this if else. At the end of, so before this ends, we must set, so before this end we must set this. So we'll pass it to a1 row and calls, yeah. So if everything is, if all the point in contention, if the ij is inside, then it will assign this definitely. It will assign also this increment n call, it will assign this increment n call, assign this increment n call, assign this increment n call. So you will have 5 such insertions. If not, if you are at the neighborhood of the left boundary, right, then this will not be executed because you've already accounted for the fact that the left boundary condition is equal to 0. If you are in the vicinity of the right boundary, so that the nearest neighbor of the I comma j is the right boundary, then you will not go into this if statement solely because of this. Okay, so this is how you can account for those end cases. All right, so here we have accounted for the end cases. We have set the values from the stencil. All right, then lastly we must do mat assembly begin a comma mat final assembly, and finally we must end this assembly as we have done before as well. End. All right, finally we must return a 0, and oops, so this assembly has to be done after both the loops are executed. So this is the end of while loop, this is the end of x loop, we must conclude with this. Let me just indent it. So it doesn't really matter. The indentation in C doesn't really bother us. Finally, we will return 0 if everything is correct. Oh, okay. So now we have all of this going on. Let us see if everything compiles. So for that, let me open up the make file. Let me create a new target. So what is the target? And the name of the file is Poisson. Control H. Control H is to replace. So try diag has to be replaced by Poisson. Replace, 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 replace. Well, we must make all the shortcuts available to us. Okay, so now let me just quickly navigate. So now we have the make file over here. So make Poisson unused variable. Okay, unused variable, that's fine. Okay, encall, there seems to be an error in encall. We've called it encalls. Well, encalls, 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 encalls. So these are some silly mistakes, but you can clearly figure it out from this. Let me compile again. Let me clear everything and compile. Yeah. So val is not val, it's simply v. I got carried away. No problem. This should be fine. Let me clear everything and compile again. This has to be a double equal to. Look, these are all errors which you make when you're writing code quickly. Look, there's no rush really. I mean, you can take your time to write a program. And now, cancel, not now. Okay, so now what we have is unused variable. We have not used info in the main. We have not used the error in the main. Dmda, what is it? Double H not used. Well, double, yeah, this is not used. So we can remove that. Tm create matrix. Where is it? Tm create matrix, line 121. So what is the issue? Oh, we must pass the address of A rather than this. I'll show you the functional reference. Tm create matrix. It will be the address of A, not A. Okay, it's star mat, meaning we have to pass the address of the matrix. Okay, some silly mistakes removed. It just goes to show that H is unused. What is it? For inform matrix. We've made a lot of errors, but that's okay. To err is human. Okay. Inform matrix. We don't need this anymore. Obviously. Now we should have only unused warnings. Great. So we have successfully debugged our little code and we have removed whatever errors we have encountered. So in the end, it's solving, and now once it is solved, how do we know it is correct? We must find out the error. So again, let's do that. So first things first, we must do u minus u exact, like in the last lecture, ax plus y, we must pass u minus 1 and u exact. We cannot, like Python, we cannot do simply u minus u exact. That's not how we can operate between two vec objects in PETSc. We must use the BLAS or the LAPAC kind of notation, ax plus y, and you will find such kinds of implementations throughout BLAS and LAPAC. All right, so then we will see vec norm, and because ax plus py stores the output in u, vec norm will have u comma norm infinity, the infinity norm, and finally we have to pass the address where to store, so address of error. So error will be the max error. Okay, so finally we can simply print out the error. So printf, or rather PETSc printf, PETSc world, because we want to print it on a single processor. Error is percentage e slash n error, and that's pretty much it. Okay, so let's compile. Now it should not show us the unused info. Oh, okay, this Dmda info is okay, so we don't care. In the main, we've declared this, but we have not used it. Anyway, doesn't matter. So after running this dot slash Poisson, it will run it with a default 9x9 grid, allow access, and it shows infinity. Well, clearly there is something wrong. So let us we have not even called the functions and we have run the program, so we need to call the functions. Okay, so form RHS this, so we need to pass dA and the vector b. Then what did we have? The matrix form matrix dA comma a, create exact, what is it, what was the function name? U exact. Okay. U exact dA comma U exact. Alright, so now let me recompile and let me run this. Okay, so there appears to be some error. Bad file descriptor. So there's an out of range issue. Let us see where we can whether we can catch it. So the segmentation fault is appearing somewhere. Let me comment out this to see whether we can isolate it, whether it's happening over here or not. Okay. This is a very silly mistake that we did. Before going into this loop, we should have told that we want to link U exact with the auxiliary vector that we want to define on the grid. So we must definitely do this particular line. This is quite important. So dmda vec get array, and that's why it was throwing a segmentation fault, because it doesn't know what to do with the pointer. It's simply lost. So dau exact and the address of au exact. Alright, similarly we must do this for this thing as well. So over here it will be b and ampersand ab, because otherwise it doesn't know how to, because once we are restoring we have to get that as well, and we have seen this in the one of the previous lectures as well. Okay, have we done it for the matrix? Okay, let's see whether it compiles. There's some, yeah, we forgot about this. Okay, everything seems to run, but still we have an error. So in fact, because we have some kind of error, let us quickly try to debug it. So for that we're gonna print out the, where is the, we can print the different things. We can mat view a. Let us see, let us run this and see whether mat view works properly or not. Well, when we view the matrix, everything appears to be 0. So why is that? Why is everything 0? So let us make a small loop over here to print out the values of v that are being inserted. For int k equal to 0, k less than 5, k plus plus, f printf percentage f slash n vk. So this should help us set things straight, why that error is. So let me make this, not f printf, this has to be simply printf. I think I've completely lost it because I had commented them out. Well, I hope it runs now. Yes, and the error is 5.16 to the power minus 2. Well, there was nothing wrong. It's just that I had commented it out for debugging something else and forgot to uncomment it back. Those kind of things happen, especially when you're doing things live. Alright, let me remove the small print statement that we had done. Great. And we don't need to print the matrix as well. So yeah, that takes care of that. Let us make it, and the error is this. In fact, in the main we can tell the grid size percentage d, and corresponding to that grid size what the error is. And for fetching the grid size, what we need to do is dmda get local info, then da into info, and finally we have to print info dot mx. That is the the size of the grid, nothing else, right? So, I mean, it's equal in both directions, so it doesn't matter. So let me recompile. And so grid size is 9. So now what we can do is, uh, we can refine the grid. So minus dA refine, and what refine does is doubles the number of grid points. Okay, so refine simply doubles the number of grid points. So if I do 2, it runs the code on 33 cross 33. What does refine 4 do? 129. So grid size is 9. Okay, yeah. So if refine is 1, it will do it on a grid size of 17 and so on. So it's 9, 17, 33 and so on. So this is how we can increase the refinement. So let me refine something. Why is the error not reducing a lot? Why is the error stagnating? So let's see whether we have, so most likely it's some error in writing these functions, because we don't seem to have done anything wrong. No, that's correct. So u exact, these all should have been -1. Well, you've seen me make some mistakes, but I hope that doesn't distract you from the overall structure of the program. These all were -1s, and it pays. That is why it is always good to have a known solution, so that you know if something is going wrong or not. Yeah. So let me recompile. This time we should have it correct. Oh yes. So as we increase the refinement, the error keeps on reducing. Maybe it's too large of a grid. Let's see. Let's wait for a while. And maybe it's too large. Let me make it 6. This shouldn't take too much time on my computer. But yeah, you can see that the error is reducing. The point I want to make is, don't make silly mistakes. That is all I can say. So in this particular lecture, we've seen how to solve a Poisson equation using this Dmda, a structured grid. And once this runs, we can visualize the matrix and all that as well. Well, let's just do it for 5. And yeah, so for 5 it is this. And let me only refine it twice, and let me show you the matrix. So minus mat view, draw minus draw pause 10. Before that I have to start xming, which is the x11 forwarder for communicating, for creating graphics from this virtual sort of machine. Yeah. So this is how the pentadiagonal matrix looks like. Oops. Let me make it only 1. Maybe it's better. Yeah, this is how the pentadiagonal matrix looks like. Well, unfortunately, when I expand this, it goes away. But anyway, so you can have a look at that. And what else can I show? I can, yeah, so you can output the file. I've shown you how to output a file using fprintf, and you can plot it using Python and all. But anyway, the key point that I want to show is how to make the RHS, how to make the LHS. So now you can try to solve various kinds of partial differential equations using the Dmda construct. So finite difference methods you can easily solve. So I'm not gonna take any much of your time. We've begun we've begun making some silly mistakes, but anyway, I'll see you again next time. We're gonna do some nonlinear equations. Until then, it's goodbye. Have a good day.